We spent the last lesson designing our first state machine, and we started out with a concept, kind of went through an overall design, what the block diagram of this was, what the inputs to the system were, what the outputs were, and then we designed that state diagram. And from the state diagram, we were able to figure out how big a memory we needed to store this state in. Now, when we're talking about the size of memory, we're not talking about megabytes, kilobytes, whatever. We're talking about individual bits. So for example, if I had a state machine that had 6 states, I'd have to number them 0 to 5. 5 in binary is 101. And 101 requires 3 bits, and so we know that the limit, or the size of our memory, doesn't have to be any bigger than 3 bits. So things like that, and also then from the state diagram, we were able to come up with truth tables and the logic and so forth. But what we were really looking at was this design of a system that took this format. In the middle, we have memory. And so the memory is made up of D latches. Now I'm going to actually just put down 3 D latches here, but there could be any number of them. There could be, well, 1 D latch, or excuse me, D flip-flop. 1 D flip-flop, that would give us, well, just 2 states, 0 and 1, right? 2 D flip-flops would give us 4 states, 0, 0, 0, 1, 1, 0, 1, 1. So we could have a machine that moved through 4 states. 3 of the latches, how many? 2 to the 3, that's 8 possible patterns of 1s and 0s. So these 3 D latches, they could store up to 8 different states. Now on the input side of all these D flip-flops, I said latches again, didn't I? We have our clock inputs and our D inputs. And then on the output side, we have our cues, right? All right, so that's the general format of the memory, the core of our state machine. This is where our state is stored. So we always have this center piece that is storing memory. Now, coming out the cue bits, that's our current state. Now, with the nomenclature that I'm using to represent the state machine, what I've got is that I'm just simply going to number them S0, S1, and S2. And so those 3 bits, those represent from the least significant to the most significant the condition of our machine. Now, the state machine that we designed, that was called a Moore machine. Now, the Moore machine, there were 2 types of state machines. One of them used just the state in order to generate the output. The other one combined the current state with the inputs to the system to generate the output. The one that combines the current state with the inputs to generate the output, that's called a Mealy machine. The Moore machine, and this is the way I remember it, uses only the state to generate the output. Only output. Moore, O-O, right? Now, coming out of the state, we've got these 3 bits, and they're going to go into this block of logic that I'm going to call the output logic. And coming out of the output logic, and in this case, I'm just going to draw 1 output, but remember from our example with the previous lesson, we had, we were doing a traffic signal. I had 6 outputs there. And so these outputs here that are coming from the memory, they are driving the output logic that's going to generate some sort of an output for our system. All right, and so all of these bits, they go into the output logic to generate the output. All right, now coming into our memory, we have the next state. So these 3 bits right here, those generate, and in fact, let me go ahead and identify these. So these 3 bits right there, and it could be, as I said before, any number of bits. This is the current state. All right. Now, coming into these D latches, or these D flip-flops, did it again, I've got S2 prime, S1 prime, and S0 prime. So those primes identify this as where we are going to be going. So this is the next state. Now, those 3 bits are what is going to be stored inside of the D flip-flops when we get a clock pulse. All right. So this clock pulse, it is simply a heartbeat that defines how quickly we are going to react to any sort of changes on the input to be able to adjust the next state we're going to, how quickly we're going to take that next state and store it in. If I've got a slow clock, then that means I may have a change on the input that takes just a moment before it is actually stored, that if it's moving us to the next state, that sees that new value stored as the current state in our system. So that speed of that clock really is just telling us how quickly we're going to move from state to state to state if there are changes to be made. Now, going to the inputs, and generating this is what we're going to call next state logic. So I have some logic here that is taking the input to our system along with the current state in order to generate what our next state is going to be. And so what I've got are things like my inputs. I'll just put I sub 0 and I sub 1. So I've got my inputs, I sub 0 and I sub 1, that are being combined along with my current state. Remember, I have to take all my bits for my current state, bring those over here. If I've got room. All right. So I've got my current state along with my inputs to my system that are determining what the next state's going to be. All right. So let's take a look. Let's examine this architecture for just a moment. First of all, this system, and as I said before, we could have any number of flip-flops in the middle there. This system, we know, has at most how many states? Well, remember that each state, and those are represented in our state diagram with those vertices, the circles, right? Each state has to have a unique number that identifies it. That unique number that is being stored in memory identifies what our current state is, which one of those vertices we're in. I have 3 D flip-flops there. That's 2 to the 3 possible patterns of 1s and 0s that I can have inside of that memory, which means I can have at most 8 states. All right. So the number of states is less than or equal to 8. All right. But it turns out we also have a lower limit here, because designing it the way that we did, if we went through and numbered these states, if we decided that, let's say I had 3 states, well, 3 states would be numbered 0, 1, 2. The 2 in binary is 1, 0. 1, 0 only requires 2 bits. So if I had only had 3 states, I wouldn't have needed the third latch or for a third flip-flop. So what's the minimum number of states that we'd have? Well, 4 states would have only needed 2 flip-flops, 0, 0, 0, 1, 1, 0, 1, 1. So we know that there were at least 5 states. At least 5 states. And the reason why I say there's at least 5 states is because then we would have been numbered 0, 1, 2, 3, 4. 4 is the first pattern in binary, is the first pattern of 1s and 0s that requires 3 bits. So I know that this system, going through the design procedure that we used in the last lesson, we know that we've got more than or equal to 5 states, but less than or equal to 8 states. All right. Let's talk about something else. The truth table that generated the output logic. How many rows did that have? Well, think about it this way. The truth table has to take these 3 inputs in order to define an output. 3 inputs, 8 possible patterns of 1s and 0s, right? So we might have had, let's see if we can draw a little truth table up here, S2, S1, S0. So the truth table would have looked like this. All right, so it would have had 8 rows, right, to generate this output Y. And let's go ahead and, I don't know, we'll just make up something, right? All right, there is a sample truth table. So if I were to say, okay, I've got my diagram up here, and let's just go ahead, I'll just pick a state. How about 101? Okay, 101. That would define, well, we could look through this truth table. We know that if we had designed our logic properly, y would have equaled 0. Okay. Now, that is defined from this truth table based on the current state. And so since you should be able to design the sum of products expression using a Karnow map from this truth table, you should be able to go ahead and figure out what this output logic looks like. And this came from our state diagram. Our state diagram, each one of the vertices identifies what our output should be. So when we've numbered a vertice, a number of that would identify one of these rows in the truth table, that would have showed us what the output would be. All right. Now, in that same vein, and I'm not going to draw this truth table, how many rows would the truth table for our next state logic have? Well, there are 5 inputs there, right? So 2 to the 5th, that means there's 32 patterns of 1s and 0s. 32 patterns of 1s and 0s, that gives us a big truth table, right? But that there's 32 patterns of 1s and 0s would identify for us exactly what the next state should be. And so, I don't know, let's just give it, so we've got the current state is 1, 0, 1, right? And I don't know, some pattern of 1s and 0s for the inputs. That would generate some sort of, the truth table would identify exactly what the output of this state, this next state logic would be to give us what the next state would be. So right now we're kind of looking at a steady state, no pun intended, state machine. If there was a clock pulse right now, what would happen? Well, if there was a clock pulse right now, this 110 would be stored in memory. The 110 would then come out of the state bits right here, and that would go through the output logic, the 110, and change our output from a 0 to a 1 based on this truth table defining that logic. That 110 then would come back around here into these state bits combined with the inputs to generate what our next state would be after that. All right? So that just gives you an idea of, in general, the operation of a state machine. Yes, we designed one in the previous lesson, but I just wanted you to see the architecture of how this thing kind of all comes together whenever it comes to, well, how we do our design process. So the design process went something like this. We come up with a system level design. From it, we come up with a state diagram. The number of states in the state diagram, we number all of those states in the state diagram. After we number all the states in the state diagram, we then come and convert that state diagram into 2 sets of truth tables. One truth table to identify output logic, one truth table to identify next state logic. Use our design tools such as the Karnow map in order to come up with that logic, and we've got our system. There you go. Now, next couple of lessons, we're going to design a couple of more of these state machines.